Thank you. Thanks, Thomas and Michael, for organizing this wonderful workshop, because haptics has been always fascinating to me, although I'm not a specialist of that. My field of expertise is more contact mechanics and how we can use it to understand and manipulate friction along soft interfaces. So in this work, or in this talk, I will show you recent experimental results that we got in our lab in Lyon, in France, which is especially the PhD work of Antoine Mans. And it will be about a design strategy to be able to reach specified friction loads with soft rough interfaces. Okay, so the usual task of contact mechanics is to predict the contact state of two solids in contact. And the contact state can be contact area, but also the different strengths and stray fields, thickness, conductivity, etc. And all this as functions of the properties of the solid that we put together. And among those properties, we have the bulk properties, for example, the elastic moduli, or the fact that the solids are layered. It's, of course, the macroscopic geometry of the solids, the radius of curvature, essentially, and also the loading that you have, both normal and tangential to the interface, plus some more subtle quantities like interfacial properties, how much adhesion, how much friction, and of course the roughness, the micro roughness that we can have. Okay, so from a contact mechanics perspective, the fingertip contact can be seen as an analog of a much simpler contact, which is the contact of a soft sphere on a rigid substrate. And in those cases, these are contacts that are non-conformal in the sense that the geometries are not the same on the two sides, so that if you press more on the interface, you have more contact area. Okay? And in particular, if you take the elastic case, if you consider a smooth sphere with a linear elasticity, then there is Hertz's theory from the 19th century, connecting the area of contact A to the normal force P through a power law with an exponent 2/3. And interestingly, when we do similar experiments, you press a fingertip on a surface, then you find a very similar power law relationship between area and normal load with an exponent m, which is bracketing the 2/3 exponent from the Hertz theory. Of course, there is not a perfect agreement because the real fingertip is much more complex than this simple elastic string. Okay, now if you want to shear this Hertz contact, then it's not an instantaneous transition from stuck to slipping contact, but there is this partial slip situation in which slips nucleates at the periphery of the contact, and then there is a growing slipping zone at an annulus that will progressively invade the whole contact before it can slip macroscopically. And this is the model by Cataneo and Milvin early in the 30s and 40s, last century. Again, if you do similar things to a fingertip contact, then you find an analogous transition to full slip through the coexistence of this stuck region inside the red regions and a growing slipping region. And again, quantitatively, you don't match Cataneo and Milvin because there is roughness, because there is nonlinear elasticity, etc. Okay. One thing that is not included into Cataneo and Milvin models is that when you shear a contact, a soft contact, then you usually have a reduction of the contact strength. But if you do that on the fingertip here, we can compare image of the fingertip for no shear until full sliding. You can see that the reduction occurs on two scales. First, the macro scale here within the red pore, but also for each of those micro structures that you have in the contact, the red area here is smaller when you are full sliding. And when we do similar experiments of shearing of soft interfaces, we can find both effects also in rubber contacts. For example, here a steering plane, which reduces. And also, if you have roughness here, you zoom on each micro contact, you can see in black here, and it also reduces locally. And in this case, the origin of reduction is due to large strains in the rubber. So we can suggest that in this case also reduction is linked to the large strains that we have during ship. Okay, so those simple examples just to show you that there is a kind of qualitative analogy between contacts of fingertips and smooth rubber strips. Of course, now what is the role of roughness? We haven't talked about that yet. When you take a fingertip contact, there is roughness on both sides. Okay, so there is a roughness on your sample here, which is a texture that you would like to sense when you rub your finger on it. But on the finger itself, there is also a structure, which is fingerprints, and which divides the contacts into parallel bands with a rather well-defined period. And the existence of these fingerprints could be shown in analog experiments. Here that it's inducing or it's amplifying the vibrations that happen inside the skin where the mechanoreceptors are embedded. And this amplification of the vibrations when the finger is rubbing the surface is responsible presumably for a large enhancement of the sensitivity to fine roughness. Okay, this is fine, but if you want to control friction, you don't want to manipulate the fingers of the persons, you want to manipulate the substrate that they are touching. And this is what is usually done in psychophysics experiments, where you present well-controlled samples to a panel of persons, and you want to correlate the tactile perception they have of the surfaces to the physical properties of the surface. And of course, roughness is one of those properties, but friction is also one. And in the following, I would like to show you how you can use knowledge in contact mechanics in order to prepare samples with prescribed friction laws. Okay. This is the main objective of the talk. So soft contacts are everywhere, and usually some of them can have a key functional role in applications like in propulsion, grid, or in medicine. And these functions, they often come with very challenging specifications. For example, here for the syringe plug, you want it to seal the liquid, you want it to stay in place if you don't touch the syringe, and you also want it to move smoothly and easily if you want to actuate it. Okay, and this is not trivial for a tribology perspective. So optimizing the friction of soft contacts it remains challenging, and this is what we address in our work in our team. Okay, so let me kind of raise the research questions that we had in this work. So for a given material pair, can one design a surface roughness so that the contact interface will behave according to a predefined friction law? Okay, so in other words, can we do like in the metamaterial field? So we start with the target macro scale behavior, which is friction law. Well, friction law here, I consider the evolution of the friction force as a function of the normal force on the interface. It can be this curve, for example. And now we want to be able to manipulate some relevant micro scale or microstructure of the system, which is now the micro roughness, so that when you put those two surfaces together, we get exactly the friction law that we wanted at the beginning. Okay. This slide to remind you that usual interfaces, they obey the linear friction law, okay, so-called Coulomb friction, meaning that the friction force is proportional to the normal force, and the slope of this law is the so-called friction coefficient mu. And in tribology textbooks, mu is considered as a constant for a given pair of materials. In the following, I will show you that we can tune the friction coefficient without changing the materials, just by playing on the microtopology. Okay, so fine-tuning friction is usually considered out of reach because the real interface looks like this. Okay, a lot of different length scales all coupled elastically together, plus a lot of interacting physical phenomena. So if you want to control anything in that, my claim is that you first need to simplify the system drastically. And in fact, what we have been doing is dealing with this type of simplified interfaces. With the four hypotheses that we've done there, but deformation is available only on one of the two solids, being a soft PDMS elastomer, while the other solid is a rigid glass. Second, the roughness is only on one of the two solids, which is a soft solid. And there is a single length scale in the topography of this soft solid, because it's an array of spherical asperities, all with the same radius of curvature of. Last, they are organized according to a square lattice with an interdistance which is large enough so that we can neglect elastic interactions between individual asperities. Okay, so the design parameters that we have for this type of geometry are n+1, the number n of asperities, plus the list of their individual heights, each height for each asperity. So this is simple now, but we still need to know something about PDMS glass friction before we can predict the list of heights that we need to get a given friction law. So the first input that we used is that the friction force is proportional to the area of contact when you are sliding. Okay, F proportional to AF, and the coefficient of proportionality here is the friction stress of the interface. And this is constant for the pair of material. Okay, so from this you can see that if you want to design friction, you just need to design the contact area AF, and this is now becoming a contact mechanics question. Okay, second input is that we want to calibrate the building block of those beta interfaces, and the building block is the individual microcontact. When you press those microcontacts, then you could find that they follow very well Hertz's model for implementation with an effective Young modulus 1.4 megapascals. Okay, then now you shear these microcontacts, and as I said before, you will expect a reduction of the area. And indeed, if you look at the final area when you are sliding, then it is only a fraction B of the initial contact area that you have when you only press normally on your contact. Okay? B was calibrated to be 0.85 in our experiment. So when you put this slide with the previous one together, you can see that the friction force is proportional now to A0. So the area of contact when you press only normally to the contact. So it's even simplifying the picture. Okay, the third input is when you know the behavior of the single microcontacts, then you want an upscaling model to predict what is the macroscopic behavior of an ensemble of such asperities. And we could show that a simple type of Williamson model is enough. This is a model which considers individual asperities that are independent from each other, so they don't talk to each other. And so the macroscopic behavior, normal force and area are just sums over all n asperities. Okay, no interacting term to be considered. Of course, now the challenge is to invert this type of model, because we want to start from the friction law and go to the list of heights here and the equation. I don't show you any detail about how we did these inversions, but I will show you 3 examples in which we managed to obtain a suitable inversion, depending on the prescriptions that we had on the friction. The first example here is we wanted friction laws passing through a certain number of operating points. Second example, linear friction laws, but we wanted to tune the slope. And third example, tunable bilinear friction laws. Okay, I want to emphasize that this strategy is intended to be material independent, in the sense that it could be carried out whatever the values of the material parameters. Material parameters in our case are the Young modulus, the friction stress, and the area reduction ratio. So what we do is to divide the friction force by sigma times B, and to divide normal force by the Young modulus. When you do that, you have a rescaled friction law. And this rescaled friction law now only depends on geometrical features of your interface, radius of curvature and the list of heights. And in particular, the friction coefficient now is the equivalent of the slope of this rescaled friction law through a coefficient which is E star divided by sigma b. Okay, what do we do in practice experimentally? So very easily, we take a piece of aluminum and then we drill holes with a spherical shape with well-defined depths for each hole. And then we mold with PDMS so that we get samples, top samples with positive asperities with the desired list of heights. And then we go to our trigonometer and we measure the friction. Okay, let's come back to the three examples. Okay, so the friction law that goes through a number of operating points. An operating point here is a couple of normal force and friction force, which is a condition that we would like the friction law to go through, to be able to be accessible with our interface. So we start with choosing three operating points. Remember, I said in usual interfaces, we have a linear friction law, so all operating points are aligned in the same straight line. Here, on purpose, we chose three different points which are not aligned, which are incompatible for usual interfaces. Okay, this is a picture of the interface that we managed to design, with asperities here that you can see with our circles with colors. In the same color as the operating point that they contribute to reach. This is a zoom here in which you can see for each asperity its size, and also the black portion in the center is a real contact area for this specific asperity. Okay, so with this design, in black is a predicted friction law, the one we target. And now I show you the experimental results we got. These are the points. And as you can see, we managed to obtain experimentally a nonlinear friction law based on three different nonlinear branches, one branch per operating point that we want to reach. Okay, and we go through all operating points within the ORs in the interface. So we show you that incompatible points can anyway be reached if we design carefully the interface with a nonlinear friction. Okay, now we go to linear friction load because this is what we find usually in nature. But we want to tune the slope. So our specifications are the following. So we targeted two different slopes and we wanted to produce two different samples, one of each for these slopes. Slope ratio 1.4 about. And again, these are the experimental points. We can see that we could produce interfaces with linear friction laws with the expected slopes better than 2%. And as I was mentioning before, those slopes there connect the friction coefficient. So we can transfer to value of friction coefficient, and there are values as different as 2.4 and 1.5. And I recall that we didn't change anything to the material in contact, only the topography is different. Okay, last example, we wanted to show that we can reach unnatural friction laws that we cannot find in new interfaces. So, for example, bilinear friction laws with tunable slopes and tunable normal force for the transition between the two. Again, our prescription, so those two slopes with the slope ratio 1.75, and we wanted to create two samples with two different values of the normal force at which we transition between the two slopes with a factor of 2. Again, the results, so two samples, two colors, red and blue. Each of them, as you can see, is well bilinear with the expected slopes for both regimes. And what you can see is that the main difference is that the transition for the red is here and the transition for the blue is here. Meaning that the two samples behave identically in friction at low normal loads, but have very different friction behavior at large normal. Okay? And for each of them, we can see the slopes as two different friction coefficients. One for small normal loads, one for large normal loads, which is not seen in nature. Okay, so to wrap up, so all those examples can be seen as new tools that are available for designers of functional frictional interfaces. And in the future, we want to increase the number of such tools. We want also to broaden the breadth of material pairs that can be used in this design strategy. And also, we would like to miniaturize the asperities so that we can go closer and closer to applications. Okay, so I hope I convinced you that although we don't know everything about friction, about tribology, we still know enough in order to solve new practical problems in tribology. And we can do that through a design strategy, one of which could be the one that I presented you today. And for this type of new interfaces here, by analogy with the field of metamaterials, we propose to use meta interfaces because we can get on-demand and sometimes unnatural friction laws through careful design of the microstructure of the interface. And I'm not an expert, I said, but I was wondering if this type of interfaces could be useful for haptics research, and I would be happy to discuss that with any of you later. And with that, I leave you on open positions to continue on this topic, a PhD position and an engineer position. Thank you very much.